pollution control in general can be pretty intimidating. It's pretty complex. The regulations and what you have to meet when you throw it in, as well with, OSHA requirements, it can be pretty daunting. It's important to have somebody that actually understands those regulations, that they understand what's at stake, and that they're going to provide a product that really is going to do what they say it's going to do.
We have exhaust fans, we have scrubber systems, we can provide people with consulting services, we can provide people with incineration systems, and we can provide people with combinations of all of that. And then from a higher level, we can thoughtfully integrate pieces and parts together to give people what they need by assessing their overall process.
Filamentous provides pollution control equipment for industrial applications, for the most part in very corrosive environments. Most of our products are FRP, which is fiberglass reinforced plastic, and that's just a much better product to use when you have a corrosive airstream or a corrosive type of application.
What we do better than anyone else is basically we're able to take an application and start to finish off our complete package for whatever the customer's needs are.
We can engineer, design, and replace an old existing system. There's times we also do retrofits. If they need one of our blowers in an existing system, we're able to design and engineer a retrofit for that as well.
Problems happen in industry, so our ability to send field service techs out right away to either help them analyze what went wrong, we have those capabilities. We have the engineering in-house, we have technicians who have been working with our company for decades, so we're able to send very knowledgeable, valued service techs out to the customer to help them with those opportunities.
You can visually look at our fans compared to other competitors and see the difference if you didn't know anything about a fan. I feel we're the best in the business. Some prefer the better things, some prefer the cheaper stuff, but if you want to last longer, I think you should go this route through Filamentous.
Welcome everybody, and thank you for joining us today for Packing's Basics presented by Filamentous. My name is Mary Rusnak, and I'm the Marketing Director for Filamentous, and with me today are John Tonkowitz, Senior VP of Technology, Jay Janning, Director of Aftermarket Sales, and Craig Brackman, our Operations Manager for our manufacturing facility. While we wait here for everyone to just finish joining in and getting set up, I want to just go over a couple of basic things about our platform and also about the professional development hours that we are offering for this class. Our webinar platform is completely interactive. You can basically open and close, minimize, maximize, resize all the windows that you have on the screen right now. A recorded version of this webinar is going to be available afterward on demand, and all that interactivity is going to remain. On the top left is the media player. If you lose your sound for whatever reason, this is the first place that you need to look. Make sure that you don't have it muted, that you haven't closed out the screen. Just take a look through that. Underneath that, you will see the Q&A area. This is where you can submit questions. To keep ourselves basically on track, we're going to do all the questions at the end, but feel free to submit them at any time. If for some reason we run out of time, we can't answer all the questions, we will get back to you. You will also notice on the left-hand side our resource list. All of these are PDF files or links to a website that you can basically look at any point in time. We have the Packing Basics Guide and Reference Summary. That's something that whoever out there is going to be taking the quiz later on for the PDH certification, that's something you might find useful. In addition, we also have the presentation slides available for download at any point in time. In addition, there is the information for attendees who are looking for the PDH certificate or the unit. A state-by-state guide, so you can download that. we have information about our Telluride Tower packing and also information about the rest of our webinar schedule for the year. We do have 4 more, so feel free to go and sign up for those at any point in time. One final thing I want to talk about here on the bottom are the widgets, and I'm just going to go through them real quickly from left to right. We start with the bios, which is some information about all of us. You can also contact us individually there. The media player widget is the red one, and again, that's the one if you're having sound issues, please take a look there. Q&A tab, if you should happen to lose it, you can pull it back up. Slides view, if you lose your slide window, just click on that. If you need technical help with the webinar platform, please check the widget with the yellow question mark. Next to that is the resource list, and the aqua-colored one is our survey. We would appreciate it if you could take a couple minutes at some point in time and complete that. Next to that, contact us at any point in time. You can send us an email. If you feel like sharing this and emailing this presentation to a friend, we would love that. So that is the little paper airplane widget after that. We also would love it if you would share this via social. That is the little orange icon. Link to the Verantis EDU website is right next to that. And then the 2 last ones are for the professional development hours. The first widget with the yellow is where you can track your progress of how far along you are in completing what you need to for the course. This is also where you will go back and print your certificate at the end when you have completed everything. The final widget, the green one, is where you actually take the test. There is a quiz for this one and at the end of the presentation, and you will need to take that test to qualify for the PDH units. Just to talk a little bit about that portion, today's webinar value is 1 professional development hour or contact hour. You must be present for at least 50 minutes to actually complete the requirements for this. This is both for the live version of the program as well as the on-demand. If you get interrupted or need to leave, you can always come back to the on-demand version later on and complete it. I would try and complete everything today. It just makes it a little bit easier, but if you really have to, you can certainly do that. Verantis requires you to complete and pass the test at the end. You must get at least 8 out of 10 correct. This is something that we require. Not all states require it, but we do for you to receive the certificate. At the end, don't forget to print your certificate when you meet all the requirements. If you forget to, you can come back to the on-demand version and print it later. You should probably keep a record log of all the webinars you attend. Most states require that you do this. You can also find some spreadsheets on a lot of the state sites that will basically assist you in doing that. Verantis will hold on to these records for 6 years. If you have any questions about any of this, feel free to contact me later. My information is in the bio section as well, as you can just hit contact us. And now we're going to move into the presentation, and I'm going to pass this on to John Tonkowitz.
Thanks, Mary, and thanks to everyone for attending today's webinar. So the topics we're going to cover today will be the basics of tower packing for absorption and scrubbing applications. Specific topics will be the basic purpose of packing. We'll look at a brief history of packing, types, a basic comparative example, and also at the end a little bit about packing inspection. I do want to emphasize that this presentation is an overview and will not include a lot of detailed design, engineering calculations, etc. For those that are interested in that level of pack tower design, Verantis will be presenting a more in-depth webinar on June 22nd. So first we'll talk about the purpose of packing. The basic purpose of packing is to improve the contact or mixing between gas and liquid phases in an absorption tower. Open spray towers can be used for achieving removal and mass transfer, absorption of different contaminants. But packing helps increase the contact area, and this can reduce tower size tremendously. But at the same time, the addition of packing does create additional resistance to flow. That increases pressure drop and energy usage. So optimum packing selection should be based on achieving the required contact while also maintaining a low pressure drop. So the main purpose of tower packing is to enhance mass transfer, and that's the transfer of a component from one phase into another, which in the case of an absorber or a scrubber is typically from the gas phase into the liquid phase. So here are some typical examples of different mass transfer processes. Dissolving solids in a liquid, absorption of gases into a liquid, which is what we're talking about today in scrubber operation and absorbers. Drying is another mass transfer process, which is basically evaporation. Could be solvents or evaporation of water. Adsorption of gases onto a solid surface. This would be like for carbons and zeolite materials. And humidification is also another mass transfer process, which is still evaporation of water vapor into the air. So for mass transfer to occur, you need two or more species, and there must be a concentration gradient to drive the transfer of mass from the high concentration zone to the lower concentration zone. For an absorber or scrubber, the higher concentration zone is the gas, which contains some specific contaminant, and the lower concentration phase is the scrubbing liquid itself. The rate of mass transfer is directly proportional to the driving force for transfer and the area available for the transfer process to take place. So transfer rate is proportional to transfer area times driving force. As in most engineering equations, there's also an adjustment constant, and this is called the mass transfer coefficient. So transfer rate equals the mass transfer coefficient times the transfer area times the driving force. The mass transfer coefficient in this case would be analogous to a heat transfer coefficient when you're designing a heat exchanger. So this is the basic equation for mass transfer, with N being the amount of mass that is actually transferred per unit time. The delta C, the concentration gradient, that represents the driving force, which is required for mass transfer to occur. Again, to compare this to heat transfer, would be similar to a temperature gradient, which allows heat to transfer from a hot mass to a cold mass. The variable A, that represents the surface area or contact area between the two phases where we're trying to get mass transfer to occur. You can see from the equation that by increasing either the concentration gradient or the contact area, will increase the overall mass transfer rate. So to illustrate this principle, we can look at a very basic example, water evaporation. So if we assume that the air above the water has a humidity less than 100%, then it does have capacity to hold more water and evaporation will occur. So that provides the concentration gradient or driving force, which is basically the diffusion of water vapor molecules into the air. So at this point, we have a poll question that we'd like you to take a few seconds to answer. So which would evaporate faster, the water that's in the bucket or the water that's spread out on the surface of a floor?
Okay, I think that's probably enough time, so let's see what the result is.
Okay, pretty obvious.
Good job, everybody.
So yes, it's very obvious to all that the water on the floor will evaporate faster, and that's basically due to the increase in that contact area between the water and the air. Again, very simple example, but it illustrates the principle that we're trying to show here. So absorption or scrubbing is basically just the same process in reverse. Molecules of some compound are being transferred from the higher concentration in the gas phase into lower concentration in the liquid phase. Whereas when we were looking at before evaporation, we were transferring molecules from the liquid phase into the gas phase. So the contact area is the surface area of the liquid between the gas and the liquid. And again, the larger the amount of liquid surface area that can be exposed to the gas, the higher the rate of mass transfer or absorption will be. So as previously mentioned in the examples that we showed, you can see that you can achieve improved mass transfer by spreading out the liquid on the surface. But there's another way to achieve it also, and that's by increasing the surface area of liquid droplets. So this is an example that just illustrates that if you break up a larger liquid droplet, in this case 1,000 micron into 100 micron droplets, that you can increase the overall surface area by a full order of magnitude. And again, by increasing the surface area, we're increasing the mass transfer rate. So just to summarize those slides at the beginning here, contact or surface area is the second most important factor to achieve mass transfer after concentration gradient. You do have to have concentration gradient between the phases first, or no mass transfer will occur regardless of the amount of surface area that you have. And the purpose of packing media in wet scrubbers is to increase the contact area between the contaminated gas and the scrubbing liquid and improve that mass transfer. The effective surface area of the water is increased by either spreading it out on the packing surface and or breaking it up into smaller droplets. So next, I'm going to review just a brief history of packings. In the early chemical process industry, engineered packings were not really available. Natural materials were primarily used, things such as glass shards, different types of rock and stone, to try to increase the contact area between the gas and liquid phases. However, these kind of materials had non-uniform shapes and presented a lot of challenges when trying to predict performance. So the next step in the evolution of packings was the use of more uniform shapes such as ceramic spheres and metal cylinders, which were basically just cut sections of thin-walled tube. So at least you had a uniformity to the individual shapes. Later came the introduction of ceramic rings and saddles, which did provide increased surface area and somewhat reduced the restriction of flow. Metal paw rings, that's also actually an evolution of the ratchet ring, which added openings and bent tabs into the sides of the cylinders. Another development about this time was structured packing, which utilizes parallel sheets of corrugated material to again try to provide larger surface area for contact. And then most recently, filamentous style packings were developed, which took a completely different approach to achieve increased contact area while dramatically reducing restriction of flow. So we'll talk a little bit about the different types of packing, go into a little more detail. So there are basically three categories of packing. Extended surface packing, which is shown in the right-hand corner. It includes things like saddles and rings. Structured packing, which is the middle photo on the top. You can see the corrugated sheets. And filamentous packing, which is the right and left photos on the top row and the left and middle photos on the bottom row. So first we'll talk a little about extended surface packings with saddles and rings. They do have advantages that they work well with coarse liquid distribution. Because of the extended surface area, they tend to spread the liquid out very well. They typically are lower cost per cubic foot of packing. But they do have disadvantages. They are higher pressure drop normally, which translates to typically a larger scrubber requirement in terms of diameter. And they also are typically not as efficient, which means they actually require a larger pack depth. So at the end, you end up with a scrubber that's both larger in diameter and in height. There's quite a few varieties of structured packing. They do have the highest throughput velocity and very low pressure drop. However, they do have some disadvantages too. They are higher cost, and they're better suited for lower liquid flow applications. That's primarily because at high liquid rates, the liquid doesn't spread out very well on the packing surface. And so you get streams that actually decrease the amount of surface area that you have per unit volume of liquid. They've been primarily used successfully in the petrochemical market for distillation fractionation processes and also for cooling tower media. Third type of packing, again, is the filamentous style. The Tellerets, Tri-Pack, Land-Pack, Snowflake. The advantages here, they do have lower pressure drop, which translates to a smaller scrubber. Higher efficiency, which translates to a reduced pack depth. And I say lower relative cost, which we'll look at one of the later examples when we compare the pressure drop and the energy usage. The one disadvantage is that they do require a little more uniform liquid distribution at the top of the towers because they don't have the amount of extended surface that the other packings do, and they tend not to spread the liquid out as much. So we have another poll question now. Basically asking, do you think it really does matter what type of packing you use in the scrubber? They all do the same thing. That makes sense or not?
Okay, we'll let everybody finish up and take a look at the results for this one. All right, and let's take a look at the results. We have about 4% that say true. Doesn't really matter. They all do the same thing, and 95% about say false.
Okay, well, the majority answer, this is a pretty straightforward answer that, packings are different. They have a lot of different characteristics. They have different restrictions to flow, different characteristics in how they spread liquid and break up droplets. So really, they're not all created equal. It does make a difference. There might be some applications where they're very basic and low efficiency requirements where that doesn't seem to be the case, that the comparative differences are incremental. But in most cases, it definitely makes a difference which packing you use in your equipment. So there is a large variability on the packing types, primarily related to flow restriction and efficiency. So we'll take a look at these two key design considerations, which are packing factor and the height of a transfer unit. For comparison of flow restriction, which is related to pressure drop and to energy usage, almost all packing suppliers have specific pressure drop curves for air-water systems. However, historically, packed tower design utilized the standard pressure drop correlation, which is shown. The value of the x-axis is based on the specific physical attributes of the liquid and gas rates through the tower and their densities. And these are specific to the process and pretty much independent of the packing type. The value of the y-axis also includes physical system parameters, mass rate, density, etc. But it also includes the constant F, which is specific to the packing type, and that's called the packing factor. So the packing factor is a direct comparison of the pressure drop characteristics of different packings. As you can see from the equation, the higher the packing factor, the higher the pressure drop will be per foot of packing through the tower. So this is a brief table that indicates relative packing factor for a number of different types of packings. I think you can see why the early stone packings presented challenges and resulted in the development of the engineered style packings. That large packing factor resulted in a very, very high pressure drop through early tower designs. So I guess it would be simple to assume, if we're looking at a table like this, that the best way to select a packing would just be to pick whatever has the lowest packing factor. But we do have to consider the other side of this, which is the efficiency and performance of the packing as related to the contact area produced by the particular packing style that you're using. We'll take a look at a comparative example between extended surface packings and filamentous packings. The picture on the left is a basic plastic saddle. You can easily see how this packing does provide significant surface area. The liquid is spread out, create a liquid film for absorption. The picture on the right is what's called a super interlock saddle, which does provide some enhancement of the original saddle packing with the center openings and the jagged edges. But still, the primary method of absorption is based on the liquid film approach. The packing in this slide is the filamentous style tellerette. And you can see there's very, very little extended surface area. the way this packing is constructed. The primary mechanism for creating contact area using this type of packing is by breaking up the liquid droplets into smaller droplets, which then continually exposes the fresh liquid to the gas stream. The filamentous style packings in general actually have less physical surface area than the extended surface packings. But as we previously went over, it's the surface area of the liquid that is critical to mass transfer, not just the surface area of the packing itself. So in order to compare performance based on HTU, or height of a transfer unit, we do need to look at the basic equation that's used to determine packing depth for a given application. I mentioned before I was going to go into a lot of the math. We will have that webinar in June, and get more into detail on the engineering calculations. But we do need to look at this basic equation, which is used to determine packing depth for a given application. And that's Z equals NTU times HTU. This is known as the transfer unit method, where the required packing depth Z equals number of transfer units, which is NTU, times the height of a transfer unit, which is HTU. I'm not going to go into a detailed explanation of NTU. This is specific to the particular chemical and absorption process regardless of packing type. So this would have the same calculation. It wouldn't matter what packing type you're using. You can use the same calculation to determine NTU based on the efficiency requirements. But the important takeaway here is the bottom paragraph. Height of a transfer unit is a measure of the effectiveness of a particular packing for a mass transfer process. The more efficient the packing, the smaller the value of the HTU. So we're going to look at a basic example of ammonia scrubbing using water as a scrubbing solution. In this case, scrubber diameter is 7 foot, gas volume of 20,000 CFM, contaminant is ammonia, inlet concentration 5,000 parts per million. Removal efficiency for this example is 99.7%, which would put us down to 15 parts per million at the outlet. And the scrubbing liquid is water. So in order to use standardized HTU curves, we need to calculate the gas and liquid mass flow rates based on pounds per hour per square foot of the cross-section of the tower. So the cross-section is 38.5 feet, and basically we're converting the CFM and the GPM using density and the cross-section into the gas rate and liquid rate for the HTU curve evaluation. So this is a set of comparative HTU curves for an air ammonia water system. The red line is the HTU curve for extended surface saddle packing at an L rate of 4,000 pounds per hour per square foot. The blue line is the HTU curve for the filamentous style Tellurette packing, also at an L of 4,000 pounds per hour per square foot. The x-axis indicates the gas mass flow rate. So in this case, we're going to be looking at, I think it was 2,338 pounds per hour per square foot. So at the specific design conditions that we already used for the example, the HTU value for the saddle packing here is 2.6 feet. At the same conditions, the HTU value for the filamentous packing is 1.33 feet, or almost 50% less. So to compare these two in operation, this specific example requires an NTU of about 7.8 to achieve 99.7% efficiency. So that would be the same for the tower on the left or the tower on the right. But when you multiply the NTU by the HTU, it results in the packing depth shown. 20.3 feet required for the saddle packing, 10.4 feet for the filamentous packing. So the combination of the lower packing depth and the lower pressure drop, which again relates to packing factor, for the filamentous style packing results in more than 80% savings in operating costs. The operating costs for the tower on the left, almost $30,000 per year. The operating cost on the right, approximately $5,000 per year. That's based on average U.S. energy rate, electricity rate of 6.4 cents a kilowatt hour. So depends where you are in the country. Some places that could be much, much higher. There's a few places that it is lower. So you can see that packing selection can make a significant difference in terms of your operating costs. It's important to understand this when you start looking at cost of packing, because if you look at cost of packing as strictly as a commodity and a cost based on cubic foot, saddle packing on the left would definitely be less expensive. But the payback based on energy costs is pretty fast. When comparing similar types of packings, this example is for filamentous style, it's important to compare based on the same nominal size and to look at both pressure drop and HTU or efficiency for a given application together. A lot of times you'll see one size packing compared to a different size competitor's packing to show that pressure drop is less. And at the same time you'll see them switch the packing sizes to show that efficiency is greater. So you have to look at these two parameters together in order to compare. So in this particular case, these are three styles of filamentous packing, all the same nominal size, 3-inch. This application is for sulfur dioxide scrubbing using caustic solution. And you can see that when you compare actual efficiency and pressure drop simultaneously, it gives you a clearer picture of which packing provides the optimum design. So to summarize packing selection, first, compare packing factors in order to determine the best choice for lowest pressure drop and energy usage. Compare scrubbing performance based on specific HTU values, not surface area of the packing. I think you can see from the example shown previously, surface area of the packing does not necessarily translate to the most efficient packing. You have to look at which packing actually provides the most surface area of liquid. And then again, lastly, compare both pressure drop in conjunction with HTU to determine the optimum packing type for a given application. Okay, so now I'll turn the presentation over to Jay Janning. He's going to talk a little bit about inspection of pack towers.
Thank you, John. A very popular question that's asked is, how often should I change the packing in my scrubber tower? The answer to this is that it depends greatly upon the system operation, what type of what the packing is exposed to, and if proper maintenance is performed. There's a few things inside of a scrubber, as seen in the picture there, that should be inspected over time. Nozzles, a mist eliminator, and the sump. The packing itself, we have customers that will change their packing out every 3 months, and some customers will go as long as 10 years before they change packing out. The answer is there's no set amount of time. It depends greatly upon the process and what maintenance is performed on the scrubber. A couple of the reasons that we'll discuss on why the packing would need to be replaced. 3 of the most common are fouling, chemical degradation, and thermal damage. And we'll look at each of these 3 in more detail. First of all, fouling. The introduction of insoluble solids that are coming from the upstream process, such as particulate matter like silicate that can carry over from a thermal oxidizer, or hydrolysis can occur when contaminants that are coming from upstream come in contact with water and the chemical bond is broken. Second common is salts. If salts are present in the application and you're recycling water and not performing a blowdown, the salt concentrations can build up over time and cause buildup on the packing. Chemical scaling. One of the most common is calcium carbonate buildup, which is usually a source from hard water that's being used in the system. The calcium carbonate buildup or carbonate buildup can be prevented or reduced by doing like a regular acid cycle wash. And if VOCs are present, the growth of bacteria or fungus is a possibility. This could be treated with a biocide depending on how bad the growth is. As I mentioned before, we do have some customers who choose to go quite a few years before changing the packing. This picture shows an example of a customer who came to us who hadn't replaced their packing in 10 years. And originally their scrubber was designed to operate at about a pressure drop of 1.5 inches across the scrubber. And over time, this pressure drop continued to increase until they called us and said that they had a pressure drop measuring about 6.5 inches. After checking the nozzles and the mist eliminator, I asked them to take a picture of the packing and send it over. And the picture they sent looked like the packing was still pretty new. The scrubber is about 8 foot in diameter. The packed bed depth on this was about 5 feet. And from the top, everything looked good. So we asked them to open up the bottom access door, and just below that nice layer of packing, the bottom portion of the packing was completely fouled with a calcium carbonate buildup. At this point, it was so bad, the only option that they had to do was to replace it. So it's good to monitor temperature and pressure, maybe even pH and concentration in the scrubber, but really visual inspection is going to be the best method for monitoring your packing.
I love that example. I think that really goes to show you, and I like to refer to that as the beauty is only skin deep example, but it really does point out how easily you can take a look at just the surface and think that everything's fine, and just really truly illustrates how you have to dig in and kind of get a feel for exactly what's happening throughout the whole tower with all of the packing.
Exactly. Chemical degradation. All polymers will experience some sort of degradation during their service life. The only variable is how long it will last. This can be accelerated by exposure to high concentrations or temperature changes, which can be seen visually by discoloration or thinning. It can become embrittled and easily crushed in your hand. Visual cracks or crazing on the packing, or even softening where the shape of it is just kind of lost shape. An example of this is, a piece of packing that was polypropylene and at one time was clear or kind of an off-white color, can now be seen as more of an orange or like a light brown color where it's had chemical attack. Third type of damage is thermal damage. Operating conditions inside of a scrubber can fluctuate. Temperature spikes can occur. Heat will cause the packing to deform and lose shape. Can also be seen as discoloration or burnt looking. It's also possible too, if there's a temperature spike or you have an increase in temperature, the hot gas that's being introduced at the bottom of the scrubber, even though it will cool as it rises up, the hot gas at the bottom of the packed bed can melt or warp the packing that's at the bottom. Again, from the example we saw before, a visual inspection of the top of the scrubber might not show this, but a visual inspection at the bottom of the scrubber might show that the packing has lost its shape, it's softened, and it's starting to basically crumble under its own weight. And a picture to show thermal damage. These were ceramic saddles that were caught up in a fire and burnt and charred pretty bad, and they're ready to be replaced.
Okay, we're going to move on to some questions. We have quite a few that we're going to try and get through. We'll push the first one up here. How much can the pressure of the gas vary from the equation in slide number 31? And let me go back here and push 31 up to the screen.
The pressure of the gas itself, this is pressure drop, okay? So this is the pressure drop across the tower. So, the inlet pressure of a gas can have a wide range coming into a tower. and the outlet pressure would be the inlet pressure minus this specific pressure drop. I'm not sure if that answers the question or not. If not, send us a follow-up question, please. The question is, do you use HTU curves to determine chemical feed rates, for example? H2SO4 injection for an ammonia scrubber. You don't use HTU curves to determine chemical feed rates. Chemical feed rates are going to be based on the specific stoichiometry or chemistry. So for so many pounds of ammonia coming in, you'll need so many pounds of sulfuric acid. However, the addition of reactants, caustic, in this case sulfuric acid for ammonia, can further reduce the HTU value. So the example that we gave was a little extreme. It was water-only scrubbing. Most ammonia scrubbers do use some type of acid for scrubbing, and so the relative HTU values do decrease when you use sulfuric acid to scrub. The comparatives, though, that we were showing between packing styles still exist, just a somewhat smaller scale.
Next one here. For a given style of packing, what would be the effect of reducing gas flow on removal efficiency?
Reducing gas flow increases what we call the L to G rate, the liquid to gas ratio, and typically that's going to improve efficiency. If Mary can show slide 37, can you push that one forward, Mary?
That one?
You can see here that as the gas rate decreases, which is the G rate on the bottom axis, towards the left, the HTU value does decrease. So it's always possible to design a very, very large diameter scrubber with a lower packing depth, but that's not always very optimum from a cost standpoint. Most of the time you're trying to do just the opposite, which is designed for the smallest diameter scrubber possible to achieve your given efficiency. But when you do have height constraints, there's a number of ways to look at the design, and that's one of them. You could reduce the gas flow velocity through the tower. You could use a smaller packing style, which has a lower HTU value. Things like that can be done.
What is the maximum design temperature for packing, I believe it's a sand for FRP vessel near the bottom? Not sure if I...
The types of packings, Jay showed plastic packings, ceramic packings, there's metal packings. So obviously the maximum design temperature is going to be based on the particular material of the pack. Even the plastic materials, there's Teflon, Kynar, polypropylene, polyethylene, CPVC. They all have different temperature properties and also different structural properties, different deformation properties. So it's not always at what temperature a plastic may melt. You have to look at where those plastics start reaching a deformation point. It also comes into play as the pack depth itself. When you have a small pack depth, obviously you don't have as much weight pressing down, so you have less force. The larger the pack depth, the more force you have pressing down. That's not an exact answer to your question. In general, for our systems where we use standard polypropylene packing, we normally use 180 degrees Fahrenheit as the maximum temperature. And if we're going higher than that, then we look at alternate packing materials.
Next slide that's going to come up is mass transfer independent of pressure drop through the scrubber?
Mass transfer is somewhat dependent on pressure. Okay, the equilibrium curve for various components, which we didn't get into here, which will be part of the next webinar, is dependent on pressure. So the system is dependent on pressure. Higher pressures make it easier to get gas to go into a liquid. Lower pressures, for example, vacuum, make it easier for gases to leave a liquid. So pressure does have an impact, but the kind of pressure drops that we're talking about here over typical pack columns, which are, you know, anywhere from 2 to 6 inches, it really has minimal effect.
Next question, to minimize water usage from blowdown, what criteria are used? If conductivity or TDS, do you have guidance on typical ranges for these?
Yes, we quite frequently use conductivity when you're looking at different types of salts that are the byproducts of the particular reactions. And but the guidelines for those really are based upon your specific system. Every salt has a different solubility level. So you have to look at that particular salt or combination of salts that's in solution. And then obviously we're trying to look at operating at below their solubility point to make sure that they don't precipitate and cause buildup inside the tower.
We're going to go back to slide 31 here again. Regarding slide 31, the .075 implies that the inlet gas is normally close to atmospheric pressure.
Yes, that slide was using the standard density of air. For more involved designs, you would adjust the calculation for the density of the specific gas that you're using. This standard pressure drop correlation shown here is somewhat simplified. It's based on air and water. A more rigorous standard pressure drop correlation you'll find in a lot of chemical engineering books will include additional parameters for viscosity, for density of a specific liquid compared to water, because for example, in many applications you might be scrubbing with an alcohol or a solvent, and your gas might be at higher pressure, which would mean increased density. Or in some cases, lower pressure if you're at elevation and temperature. So when you look at a more rigorous packed tower design, the inlet gas density is very critical to determining pressure drop, just like it would be in any type of device where you have a flow restriction. Density makes a difference. Lower density is less restrictive, and higher density is going to cause more restriction.
Where is plastic ball packing used?
Plastic ball packing? I think the only place that we've seen it used is for fluidized bed scrubbers, because it's kind of similar, to go back to one of the earlier examples, the very early ceramic balls that were produced. You know, they have the surface area on the exterior, but they don't allow any flow through that. They only allow flow through the voids of between the spheres. So they're pretty restrictive to try to use just plastic balls as a standard packed tower packing. Some of the filamentous style packings are more spherical, but they're much more open.
Okay, we have time for one last question, and then we'll wrap it up. And just final reminders after this for people that are here for the PDH units, please stay on. But let's see, one final question before we finish this up. What would be a good inspection routine?
Well, I mean, semi-annually would be a good chance, you know, spring or fall. You have a scheduled shutdown to take a look at the nozzle, make sure that, you know, there's no buildup, take a visual inspection of the packing,
So typically with the pack towers, you've got a couple different things. You've got your spray nozzles, your mist eliminators, and your packing. Typically, as Jay touched on, you're going to be looking at every 6 months or so. But there are a few components like the spray nozzle. That's kind of the lifeblood of getting the liquid onto the scrubber. You may want to look at that every 3 months. But obviously, it is based on your shutdown schedule too.
Well, it's also to some degree it's based on application. There are certain applications that are just dirtier by nature, and so in some cases we would recommend even shorter inspection cycles.
Okay, we are out of time here. If we did not get to your question, we will get back to you. So don't worry, we will get in touch with you with anything that hasn't been answered. If you are not here for the PDH units and just for the webinar itself, I just want to thank you for coming and hope you will sign up. We have 4 more scheduled here for the rest of the year. We'd love to have you attend. If you are here for the PDH, just want to remind you that you need to go to the last 2 widgets in the bottom of the screen. The yellow one will tell you if you have met the requirements. Basically, you have to have been online for 50 minutes. We have certainly met that if you've been here from the beginning. If you haven't, if you came in late, you will have to go back and complete the allotted time requirements. You also need to pass the test, which is the green widget on the end, the very last one. So make sure that you take both of those. Just a reminder, over in the resource list, the basic packing guide and reference summary can help you along there if you're having any trouble with some of the answers. But once you are done with both, please go to the yellow widget and you can print out your certificate there. If you have any problems, feel free to contact me. All of you have my information, mary.rusnak@verantis.com. And I want to thank you all for joining us, and we hope that you as well will come back and do some more of them. You can pre-register for the rest of the webinars for the year. They do all offer 1 PDH unit. We are going to turn the sound off at this point, but the platform itself will be running until 1:30. That gives you all a chance to finish up the quiz and print out your certificates and print out any additional resources that you like. After this, the recorded version will be available on demand. Usually takes about half a day to a day to come back, and you will get a link with that information. But definitely feel free to forward this on to anybody else who you think needs these credits or just might need this information. But otherwise, I hope you have a wonderful week, and thank you again for coming.